Universe defined. The universe, Latin, universus, is all of space and time and their contents, including planets, stars, galaxies, and all other forms of matter and energy. The Big Bang theory is the prevailing cosmological description of the development of the universe. According to this theory, space and time emerged together 13.7 20 billion years ago, and the universe has been expanding ever since the Big Bang. While the spatial size of the entire universe is unknown, it is possible to measure the size of the observable universe, which is approximately 93 billion light-years in diameter at the present day. Some of the earliest cosmological models of the universe were developed by ancient Greek and Indian philosophers and were geocentric, placing Earth at the center. Over the centuries, more precise astronomical observations led Nicolaus Copernicus to develop the heliocentric model with the Sun at the center of the solar system. In developing the law of universal gravitation, Isaac Newton built upon Copernicus's work as well as Johannes Kepler's laws of planetary motion and observations by Tycho Brahe. Further observational improvements led to the realization that the Sun is one of a few hundred billion stars in the Milky Way, which is one of a few hundred billion galaxies in the universe. Many of the stars in a galaxy have planets. At the largest scale, galaxies are distributed uniformly and the same in all directions, meaning that the universe has neither an edge nor a center. At smaller scales, galaxies are distributed in clusters and superclusters, which form immense filaments and voids in space, creating a vast foam-like structure. Discoveries in the early 20th century have suggested that the universe had a beginning and that space has been expanding since then at an increasing rate. According to the Big Bang theory, the energy and matter initially present have become less dense as the universe expanded. After an initial accelerated expansion, called the inflationary epoch at around 1032 seconds, and the separation of the four known fundamental forces, the universe gradually cooled and continued to expand, allowing the first subatomic particles and simple atoms to form. Dark matter gradually gathered, forming a foam-like structure of filaments and voids under the influence of gravity. Giant clouds of hydrogen and helium were gradually drawn to the places where dark matter was most dense, forming the first galaxies, stars, and everything else seen today. From studying the movement of galaxies, it has been discovered that the universe contains much more matter than is accounted for by visible objects, stars, galaxies, nebulas, and interstellar gas. This unseen matter is known as dark matter. Dark means that there is a wide range of strong indirect evidence that it exists, but we have not yet detected it directly. The CDM model is the most widely accepted model of the universe. It suggests that about 69.2%, 1.2%, 2015 of the mass and energy in the universe is a cosmological constant, or, in extensions to CDM, other forms of dark energy, such as a scalar field which is responsible for the current expansion of space, and about 25.8%, 1.1%, 2015 is dark matter. Ordinary baryonic matter is therefore only 4.84%, 0.1%, 2015 of the physical universe. Stars, planets, and visible gas clouds only form about 6% of the ordinary matter. There are many competing hypotheses about the ultimate fate of the universe and about what, if anything, preceded the Big Bang, while other physicists and philosophers refuse to speculate, doubting that information about prior states will ever be accessible. Some physicists have suggested various multiverse hypotheses, in which our universe might be one among many universes that likewise exist. Definition: the physical universe is defined as all of space and time collectively referred to as spacetime and their contents. Such contents comprise all the energy in its various forms, including electromagnetic radiation and matter, and therefore planets, moons, stars, galaxies and the contents of intergalactic space. The universe also includes the physical laws that influence energy and matter, such as conservation laws, classical mechanics, and relativity. The universe is often defined as the totality of existence, or everything that exists, everything that has existed, and everything that will exist. In fact, some philosophers and scientists support the inclusion of ideas and abstract concepts such as mathematics and logic in the definition of the universe. The word universe may also refer to concepts such as the cosmos, the world, and nature. Etymology. The word universe derives from the Old French word univers, which in turn derives from the Latin word universum. The Latin word was used by Cicero and later Latin authors in many of the same senses as the modern English word is used. Synonyms. A term for universe among the ancient Greek philosophers from Pythagoras onwards was tau letter 1f78 pi letter 1fb6 nu to pan the all, defined as all matter and all space, and tau letter 1f78 letter 1f45 lambda omicron nu to hol on all things, which did not necessarily include the void. Another synonym was letter 1f41 kappa omicron sigma mu omicron sigma ho cosmos, meaning the world, the cosmos. Synonyms are also found in Latin authors totum, mundus, natura, and survive in modern languages, e.g. the German words das all, Weltall, and nature for universe. The same synonyms are found in English, such as everything as in the theory of everything, the cosmos as in cosmology, the world as in the many worlds interpretation, and nature as in natural laws or natural philosophy. Chronology and the Big Bang. The prevailing model for the evolution of the universe is the Big Bang theory. The Big Bang model states that the earliest state of the universe was an extremely hot and dense one, and that the universe subsequently expanded and cooled. The model is based on general relativity and on simplifying assumptions such as the homogeneity and isotropy of space. A version of the model with a cosmological constant lambda and cold dark matter, known as the lambda CDM model, is the simplest model that provides a reasonably good account of various observations about the universe. The Big Bang model accounts for observations such as the correlation of distance and redshift of galaxies, the ratio of the number of hydrogen to helium atoms, and the microwave radiation background. The initial hot, dense state is called the Planck epoch, a brief period extending from time 0 to 1 Planck time unit of approximately 10⁻43 seconds. During the Planck epoch, all types of matter and all types of energy were concentrated into a dense state, and gravity, currently the weakest by far of the four known forces, is believed to have been as strong as the other fundamental forces, and all the forces may have been unified. Since the Planck epoch, space has been expanding to its present scale, with a very short but intense period of cosmic inflation believed to have occurred within the first 10⁻32 seconds. This was a kind of expansion different from those we can see around us today. Objects in space did not physically move, instead the metric that defines space itself changed. Although objects in spacetime cannot move faster than the speed of light, this limitation does not apply to the metric governing spacetime itself. This initial period of inflation is believed to explain why space appears to be very flat and much larger than light could travel since the start of the universe. Within the first fraction of a second of the universe's existence, the four fundamental forces had separated. As the universe continued to cool down from its inconceivably hot state, various types of subatomic particles were able to form in short periods of time known as the quark epoch, the Hadron epoch, and the Lepton epoch. Together, these epochs encompassed less than 10 seconds of time following the Big Bang. These elementary particles associated stably into ever larger combinations, including stable protons and neutrons, which then formed more complex atomic nuclei through nuclear fusion. This process known as Big Bang nucleosynthesis, only lasted for about 17 minutes and ended about 20 minutes after the Big Bang, so only the fastest and simplest reactions occurred. About 25% of the protons and all the neutrons in the universe by mass were converted to helium, with small amounts of deuterium, a form of hydrogen, and traces of lithium. Any other element was only formed in very tiny quantities. The other 75% of the protons remained unaffected as hydrogen nuclei. After nucleosynthesis ended, the universe entered a period known as the photon epoch. During this period, the universe was still far too hot for matter to form neutral atoms, so it contained a hot, dense, foggy plasma of negatively charged electrons, neutral neutrinos, and positive nuclei. After about 377,000 years, the universe had cooled enough that electrons and nuclei could form the first stable atoms. This is known as recombination for historical reasons. In fact, electrons and nuclei were combining for the first time. Unlike plasma, neutral atoms are transparent to many wavelengths of light. So for the first time, the universe also became transparent. The photons released decoupled when these atoms formed can still be seen today. They form the cosmic microwave background CMB. As the universe expands, the energy density of electromagnetic radiation decreases more quickly than does that of matter because the energy of a photon decreases with its wavelength. At around 47,000 years, the energy density of matter became larger than that of photons and neutrinos, and began to dominate the large-scale behavior of the universe. This marked the end of the radiation-dominated era and the start of the matter-dominated era. In the earliest stages of the universe, tiny fluctuations within the universe's density led to concentrations of dark matter gradually forming. Ordinary matter, attracted to these by gravity, formed large gas clouds and eventually stars and galaxies where the dark matter was most dense and voids where it was least dense. After around 100–300 million years, the first stars formed, known as population Roman III stars. These were probably very massive, luminous, non-metallic, and short-lived. They were responsible for the gradual reionization of the universe between about 200–500 million years and 1 billion years, and also for seeding the universe with elements heavier than helium through stellar nucleosynthesis. The universe also contains a mysterious energy, possibly a scalar field called dark energy, the density of which does not change over time. After about 9.8 billion years, the universe had expanded sufficiently so that the density of matter was less than the density of dark energy, marking the beginning of the present dark energy-dominated era. In this era, the expansion of the universe is accelerating due to dark energy. Physical properties. Of the four fundamental interactions, gravitation is the dominant at astronomical length scales. Gravity's effects are cumulative. By contrast, the effects of positive and negative charges tend to cancel one another, making electromagnetism relatively insignificant on astronomical length scales. The remaining two interactions, the weak and strong nuclear forces, decline very rapidly with distance. Their effects are confined mainly to subatomic length scales. The universe appears to have much more matter than antimatter, and a symmetry possibly related to the CP violation. This imbalance between matter and antimatter is partially responsible for the existence of all matter existing today, since matter and antimatter, if equally produced at the Big Bang, would have completely annihilated each other and left only photons as a result of their interaction. The universe also appears to have neither net momentum nor angular momentum, which follows accepted physical laws if the universe is finite. These laws are Gauss's law and the non-divergence of the stress-energy-momentum pseudotensor. Size and regions. According to the general theory of relativity, far regions of space may never interact with ours even in the lifetime of the universe due to the finite speed of light and the ongoing expansion of space. For example, radio messages sent from Earth may never reach some regions of space. Even if the universe were to exist forever, space may expand faster than light can traverse it. The spatial region that can be observed with telescopes is called the observable universe, which depends on the location of the observer. The proper distance of the distance as would be measured at a specific time, including the present between Earth and the edge of the observable universe, is 46 billion light-years, 14 billion parsecs, making the diameter of the observable universe about 93 billion light-years, 28 billion parsecs. The distance the light from the edge of the observable universe has traveled is very close to the age of the universe times the speed of light, 13.8 billion light-years, 4.2 times 10^9 pc, but this does not represent the distance at any given time because the edge of the observable universe and the Earth have since moved further apart. For comparison, the diameter of a typical galaxy is 30,000 light-years, 9,198 parsecs, and the typical distance between two neighboring galaxies is 3 million light-years, 919.8 kiloparsecs. As an example, the Milky Way is roughly 100,000 180,000 light-years in diameter, and the nearest sister galaxy to the Milky Way, the Andromeda Galaxy, is located roughly 2.5 million light-years away. Because we cannot observe space beyond the edge of the observable universe, it is unknown whether the size of the universe in its totality is finite or infinite. Estimates suggest that the whole universe, if finite, must be more than 250 times larger than a Hubble sphere. Some disputed estimates for the total size of the universe, if finite, reach as high as 10^10^122 \displaystyle 10^10^122 megaparsecs, as implied by a suggested resolution of the no-boundary proposal. Age and expansion. Assuming that the lambda-CDM model is correct, the measurements of the parameters using a variety of techniques by numerous experiments yield a best value of the age of the universe at 13.799 plus or minus 0.21 billion years as of 2015. Over time, the universe and its contents have evolved. For example, the relative population of quasars in galaxies has changed and space itself has expanded. Due to this expansion, scientists on Earth can observe the light from a galaxy 30 billion light-years away even though that light has traveled for only 13 billion years. The very space between them has expanded. This expansion is consistent with the observation that the light from distant galaxies has been redshifted. The photons emitted have been stretched to longer wavelengths and lower frequency during their journey. Analyses of type Ia supernovae indicate that the spatial expansion is accelerating. The more matter there is in the universe, the stronger the mutual gravitational pull of the matter. If the universe were too dense, then it would recollapse into a gravitational singularity. However, if the universe contained too little matter, then the self-gravity would be too weak for astronomical structures like galaxies or planets to form. Since the Big Bang, the universe has expanded monotonically. Perhaps unsurprisingly, our universe has just the right mass energy density, equivalent to about 5 protons per cubic meter, which has allowed it to expand for the last 13.8 billion years, giving time to form the universe as observed today. There are dynamical forces acting on the particles in the universe which affect the expansion rate. Before 1998, it was expected that the expansion rate would be decreasing as time went on due to the influence of gravitational interactions in the universe, and thus there is an additional observable quantity in the universe called the deceleration parameter, which most cosmologists expected to be positive and related to the matter density of the universe. In 1998, the deceleration parameter was measured by two different groups to be negative approximately 0.55, which technically implies that the second derivative of the cosmic scale factor of \displaystyle\d dot has been positive in the last 5 - 6 billion years. This acceleration does not, however, imply that the Hubble parameter is currently increasing. See deceleration parameter for details. Spacetime. Spacetimes are the arenas in which all physical events take place. The basic elements of spacetimes are events. In any given spacetime, an event is defined as a unique position at a unique time. A spacetime is the union of all events in the same way that a line is the union of all of its points, formally organized into a manifold. Events such as matter and energy bend spacetime. Curved spacetime, on the other hand, forces matter and energy to behave in a certain way. There is no point in considering one without the other. The universe appears to be a smooth spacetime continuum consisting of 3 spatial dimensions and 1 temporal time dimension. An event in the spacetime of the physical universe can therefore be identified by a set of 4 coordinates x, y, z, t. On average, space is observed to be very nearly flat with a curvature close to 0, meaning that Euclidean geometry is empirically true with high accuracy throughout most of the universe. Spacetime also appears to have a simply connected topology, in analogy with a sphere, at least on the length scale of the observable universe. However, present observations cannot exclude the possibilities that the universe has more dimensions, which is postulated by theories such as the string theory, and that its spacetime may have a multiply connected global topology, in analogy with the cylindrical or toroidal topologies of 2-dimensional spaces. The spacetime of the universe is usually interpreted from a Euclidean perspective, with space as consisting of 3 dimensions and time as consisting of 1 dimension, the 4th dimension. By combining space and time into a single manifold called Minkowski space, physicists have simplified a large number of physical theories, as well as described in a more uniform way the workings of the universe at both the supergalactic and subatomic levels. Spacetime events are not absolutely defined spatially and temporally, but rather are known to be relative to the motion of an observer. Minkowski space approximates the universe without gravity. The pseudo-Riemannian manifolds of general relativity describe spacetime with matter and gravity. Shape. General relativity describes how spacetime is curved and bent by mass and energy gravity. The topology, or geometry of the universe, includes both local geometry in the observable universe and global geometry. Cosmologists often work with a given space-like slice of spacetime called the comoving coordinates. The section of spacetime which can be observed is the backward light cone, which delimits the cosmological horizon. The cosmological horizon, also called the particle horizon or the light horizon, is the maximum distance from which particles can have traveled to the observer in the age of the universe. This horizon represents the boundary between the observable and the unobservable regions of the universe. The existence, properties, and significance of a cosmological horizon depend on the particular cosmological model. An important parameter determining the future evolution of the universe theory is the density parameter, omega, defined as the average matter density of the universe divided by a critical value of that density. This selects one of 3 possible geometries depending on whether omega is equal to, less than, or greater than 1. These are called, respectively, the flat, open, and closed universes. Observations, including the Cosmic Background Explorer (COBE), Wilkinson Microwave Anisotropy Probe WMAP, and Planck maps of the CMB, suggest that the universe is infinite in extent with a finite age as described by the Friedmann-Lemaitre-Robertson-Walker FLRW models. These FLRW models thus support inflationary models and the standard model of cosmology, describing a flat, homogeneous universe presently dominated by dark matter and dark energy. Support of life. The universe may be fine-tuned. The fine-tuned universe hypothesis is the proposition that the conditions that allow the existence of observable life in the universe can only occur when certain universal fundamental physical constants lie within a very narrow, so that if any of several fundamental constants were only slightly different, the universe would have been unlikely to be conducive to the establishment and development of matter, astronomical structures, elemental diversity, or life as it is understood. The proposition is discussed among philosophers, scientists, theologians, and proponents of creationism. Composition. The universe is composed almost completely of dark energy, dark matter, and ordinary matter. Other contents are electromagnetic radiation estimated to constitute from 0.5% to close to 0.1% of the total mass energy of the universe and antimatter. The proportions of all types of matter and energy have changed over the history of the universe. The total amount of electromagnetic radiation generated within the universe has decreased by 1/2 in the past 2 billion years. Today, ordinary matter, which includes atoms, stars, galaxies, and life, accounts for only 4.9% of the contents of the universe. The present overall density of this type of matter is very low, roughly 4.5 times 10⁻31 grams per cubic centimeter, corresponding to a density of the order of only 1 proton for every 4 cubic meters of volume. The nature of both dark energy and dark matter is unknown. Dark matter, a mysterious form of matter that has not yet been identified, accounts for 26.8% of the cosmic contents. Dark energy, which is the energy of empty space and is causing the expansion of the universe to accelerate, accounts for the remaining 68.3% of the contents. Matter, and dark energy are distributed homogeneously throughout the universe over length scales longer than 300 million light years or so. However, over shorter length scales, matter tends to clump hierarchically. Many atoms are condensed into stars, most stars into galaxies, most galaxies into clusters, superclusters, and finally, large-scale galactic filaments. The observable universe contains as many as 200 billion galaxies and, overall, as many as an estimated 1 × 10^24 stars more stars than all the grains of sand on planet Earth. Typical galaxies range from dwarfs with SQ as 10,107 stars up to giants with 1,010,12 stars. Between the larger structures are voids, which are typically 10⁻150 mpc 33 million-490 million Li in diameter. The Milky Way is in the local group of galaxies, which in turn is in the Laniakea supercluster. This supercluster spans over 500 million light years, while the local group spans over 10 million light years. The universe also has vast regions of relative emptiness. The largest known void measures 1.8 billion Li 550 mpc across. The observable universe is isotropic on scales significantly larger than superclusters, meaning that the statistical properties of the universe are the same in all directions as observed from Earth. The universe is bathed in highly isotropic microwave radiation that corresponds to a thermal equilibrium blackbody spectrum of roughly 2.72,548 kelvins. The hypothesis that the large-scale universe is homogeneous and isotropic is known as the cosmological principle. A universe that is both homogeneous and isotropic looks the same from all vantage points and has no center. Dark energy. An explanation for why the expansion of the universe is accelerating remains elusive. It is often attributed to dark energy, an unknown form of energy that is hypothesized to permeate space. On a mass-energy equivalence basis, The density of dark energy tilde 7 times 10 minus 30 G/cm3 is much less than the density of ordinary matter or dark matter within galaxies. However, in the present dark energy era, it dominates the mass energy of the universe because it is uniform across space. Two proposed forms for dark energy are the cosmological constant, a constant energy density filling space homogeneously, and scalar fields such as quintessence or moduli, dynamic quantities whose energy density can vary in time and space. Contributions from scalar fields that are constant in space are usually also included in the cosmological constant. The cosmological constant can be formulated to be equivalent to vacuum energy. Scalar fields having only a slight amount of spatial inhomogeneity would be difficult to distinguish from a cosmological constant. Dark matter. Dark matter is a hypothetical kind of matter that is invisible to the entire electromagnetic spectrum, but which accounts for most of the matter in the universe. The existence and properties of dark matter are inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Other than neutrinos, a form of hot dark matter has not been detected directly, making it one of the greatest mysteries in modern astrophysics. Dark matter neither emits nor absorbs light or any other electromagnetic radiation at any significant level. Dark matter is estimated to constitute 26.8% of the total mass energy and 84.5% of the total matter in the universe. Ordinary matter. The remaining 4.9% of the mass energy of the universe is ordinary matter, that is, atoms, ions, electrons, and the objects they form. This matter includes stars, which produce nearly all of the light we see from galaxies, as well as interstellar gas in the interstellar and intergalactic media, planets, and all the objects from everyday life that we can bump into, touch, or squeeze. As a matter of fact, the great majority of ordinary matter in the universe is unseen, since visible stars and gas inside galaxies and clusters account for less than 10% of the ordinary matter contribution to the mass energy density of the universe. Ordinary matter commonly exists in 4 states or phases: solid, liquid, gas, and plasma. However, advances in experimental techniques have revealed other previously theoretical phases, such as Bose-Einstein condensates and fermionic condensates. Ordinary matter is composed of 2 types of elementary particles, quarks and leptons. For example, the proton is formed of 2 up quarks and 1 down quark, the neutron is formed of 2 down quarks and 1 up quark, and the electron is a kind of lepton. An atom consists of an atomic nucleus made up of protons and neutrons, and electrons that orbit the nucleus. Because most of the mass of an atom is concentrated in its nucleus, which is made up of baryons, astronomers often use the term baryonic matter to describe ordinary matter, although a small fraction of this baryonic matter is electrons. Soon after the Big Bang, primordial protons and neutrons formed from the quark, gluon plasma of the early universe as it cooled below 2 trillion degrees. A few minutes later, in a process known as Big Bang nucleosynthesis, nuclei formed from the primordial protons and neutrons. This nucleosynthesis formed lighter elements, those with small atomic numbers up to lithium and beryllium, but the abundance of heavier elements dropped off sharply with increasing atomic number. Some boron may have been formed at this time, but the next heavier element, carbon, was not formed in significant amounts. Big Bang nucleosynthesis shut down after about 20 minutes due to the rapid drop in temperature and density of the expanding universe. Subsequent formation of heavier elements resulted from stellar nucleosynthesis and supernova nucleosynthesis. Particles. Ordinary matter and the forces that act on matter can be described in terms of elementary particles. These particles are sometimes described as being fundamental since they have an unknown substructure, and it is unknown whether or not they are composed of smaller and even more fundamental particles. Of central importance is the Standard Model, a theory that is concerned with electromagnetic interactions and the weak and strong nuclear interactions. The Standard Model is supported by the experimental confirmation of the existence of particles that compose matter quarks and leptons, and their corresponding antimatter jewels, as well as the force particles that mediate interactions, the photon, the W and Z bosons, and the gluon. The Standard Model predicted the existence of the recently discovered Higgs boson, a particle that is a manifestation of a field within the universe that can endow particles with mass. Because of its success in explaining a wide variety of experimental results, the Standard Model is sometimes regarded as a theory of almost everything. The Standard Model does not, however, accommodate gravity. A true force-particle theory of everything has not been attained. Hadrons. A hadron is a composite particle made of quarks held together by the strong force. Hadrons are categorized into two families, baryons such as protons and neutrons made of three quarks, and mesons such as pions made of one quark and one antiquark. Of the hadrons, protons are stable, and neutrons bound within atomic nuclei are stable. Other hadrons are unstable under ordinary conditions and are thus insignificant constituents of the modern universe. From approximately 10⁻⁶ seconds after the Big Bang, during a period is known as the Hadron epoch, the temperature of the universe had fallen sufficiently to allow quarks to bind together into hadrons, and the mass of the universe was dominated by hadrons. Initially, the temperature was high enough to allow the formation of hadron/antihadron pairs which kept matter and antimatter in thermal equilibrium. However, as the temperature of the universe continued to fall, hadron/antihadron pairs were no longer produced. Most of the hadrons and antihadrons were then eliminated in particle-antiparticle annihilation reactions, leaving a small residual of hadrons by the time the universe was about 1 second old. Leptons. A lepton is an elementary, half-integer spin particle that does not undergo strong interactions but is subject to the Pauli exclusion principle. No two leptons of the same species can be in exactly the same state at the same time. Two main classes of leptons exist: charged leptons, also known as the electron-like leptons, and neutral leptons, better known as neutrinos. Electrons are stable and the most common charged lepton in the universe, whereas muons and taus are unstable particles that quickly decay after being produced in high-energy collisions, such as those involving cosmic rays or carried out in particle accelerators. Charged leptons can combine with other particles to form various composite particles such as atoms and positronium. The electron governs nearly all of chemistry, as it is found in atoms and is directly tied to all chemical properties. Neutrinos rarely interact with anything and are consequently rarely observed. Neutrinos stream throughout the universe but rarely interact with normal matter. The Lepton epoch was the period in the evolution of the early universe in which the leptons dominated the mass of the universe. It started roughly 1 second after the Big Bang, after the majority of hadrons and antihadrons annihilated each other at the end of the Hadron epoch. During the Lepton epoch, the temperature of the universe was still high enough to create lepton/antilepton pairs, so leptons and antileptons were in thermal equilibrium. Approximately 10 seconds after the Big Bang, the temperature of the universe had fallen to the point where lepton/antilepton pairs were no longer created. Most leptons and antileptons were then eliminated in annihilation reactions, leaving a small residue of leptons. The mass of the universe was then dominated by photons as it entered the following photon epoch. Photons. A photon is the quantum of light and all other forms of electromagnetic radiation. It is the force carrier for the electromagnetic force, even when static via virtual photons. The effects of this force are easily observable at the microscopic and at the macroscopic level because the photon has zero rest mass. This allows long-distance interactions. Like all elementary particles, photons are currently best explained by quantum mechanics and exhibit wave-particle duality, exhibiting properties of waves and of particles. The photon epoch started after most leptons and anti-leptons were annihilated at the end of the lepton epoch, about 10 seconds after the Big Bang. Atomic nuclei were created in the process of nucleosynthesis, which occurred during the first few minutes of the photon epoch. For the remainder of the photon epoch, the universe contained a hot dense plasma of nuclei, electrons and photons. About 380,000 years after the Big Bang, the temperature of the universe fell to the point where nuclei could combine with electrons to create neutral atoms. As a result, photons no longer interacted frequently with matter and the universe became transparent. The highly redshifted photons from this period form the cosmic microwave background. Tiny variations in temperature and density detectable in the CMB were the early seeds from which all subsequent structure formation took place. Cosmological models. Historical conceptions. Historically, there have been many ideas of the cosmos, cosmologies, and its origin, cosmogonies. Theories of an impersonal universe governed by physical laws were first proposed by the Greeks and Indians. Ancient Chinese philosophy encompassed the notion of the universe, including both all of space and all of time. Over the centuries, improvements in astronomical observations and theories of motion and gravitation led to ever more accurate descriptions of the universe. The modern era of cosmology began with Albert Einstein's 1915 general theory of relativity, which made it possible to quantitatively predict the origin, evolution, and conclusion of the universe as a whole. Most modern, accepted theories of cosmology are based on general relativity and, more specifically, the predicted Big Bang. Mythologies. Many cultures have stories describing the origin of the world and universe. Cultures generally regard these stories as having some truth. There are, however, many differing beliefs in how these stories apply amongst those believing in a supernatural origin, ranging from a god directly creating the universe as it is now to a god just setting the wheels in motion, for example, via mechanisms such as the Big Bang and evolution. Ethnologists and anthropologists who study myths have developed various classification schemes for the various themes that appear in creation stories. For example, in one type of story, the world is born from a world egg. Such stories include the Finnish epic poem Kalevala, the Chinese story of Pangu, or the Indian Brahmanda Purana. In related stories, the universe is created by a single entity emanating or producing something by him or herself, as in the Tibetan Buddhism concept of Adi Buddha, the ancient Greek story of Gaia Mother Earth, the Aztec goddess Coatlicue myth, the ancient Egyptian god Aten story, and the Judeo-Christian Genesis creation narrative in which the Abrahamic God created the universe. In another type of story, the universe is created from the union of male and female deities, as in the Maori story of Rangi and Papa. In other stories, the universe is created by crafting it from pre-existing materials, such as the corpse of a dead goddess from Tiamat in the Babylonian epic Enuma Elish, or from the giant Ymir in Norse mythology, or from chaotic materials, as in Izanagi and Izanami in Japanese mythology. In other stories, the universe emanates from fundamental principles, such as Brahman and Prakriti, the creation myth of the Suras, or the yin and yang of the Tao. Philosophical models. The pre-Socratic Greek philosophers and Indian philosophers developed some of the earliest philosophical concepts of the universe. The earliest Greek philosophers noted that appearances can be deceiving and sought to understand the underlying reality behind the appearances. In particular, they noted the ability of matter to change forms, e.g., ice to water to steam, and several philosophers propose that all the physical materials in the world are different forms of a single primordial material, or archie. The first to do so was Thales, who proposed this material to be water. Thales' student Anaximander proposed that everything came from the limitless aperon. Anaximenes proposed the primordial material to be air on account of its perceived attractive and repulsive qualities that cause the archie to condense or dissociate into different forms. Anaxagoras proposed the principle of nous mind, while Heraclitus proposed fire and spoke of logos. Empedocles proposed the elements to be earth, water, air, and fire. His four-element model became very popular. Like Pythagoras, Plato believed that all things were composed of number, with Empedocles' elements taking the form of the Platonic solids. Democritus and later philosophers, most notably Eusebius, proposed that the universe is composed of indivisible atoms moving through a void vacuum, although Aristotle did not believe that to be feasible because air, like water, offers resistance to motion. Air will immediately rush in to fill a void, and moreover, without resistance, it would do so indefinitely fast. Although Heraclitus argued for eternal change, his contemporary Parmenides made the radical suggestion that all change is an illusion, that the true underlying reality is eternally unchanging and of a single nature. Parmenides denoted this reality as tel letter 1f7 letter 1f10 nu the one. Parmenides' idea seemed implausible to many Greeks, but his student Zeno of Elea challenged them with several famous paradoxes. Aristotle responded to these paradoxes by developing the notion of a potential countable infinity as well as the infinitely divisible continuum. Unlike the eternal and unchanging cycles of time, he believed that the world is bounded by the celestial spheres and that cumulative stellar magnitude is only finitely multiplicative. The Indian philosopher Kannada, founder of the Vaisheshika school, developed a notion of atomism and proposed that light and heat were varieties of the same substance. In the 5th century A.D., the Buddhist atomist philosopher Dignaga proposed atoms to be point-sized, durationless, and made of energy. They denied the existence of substantial matter and proposed that movement consisted of momentary flashes of a stream of energy. The notion of temporal finitism was inspired by the doctrine of creation shared by the three Abrahamic religions, Judaism, Christianity, and Islam. The Christian philosopher John Philoponus presented the philosophical arguments against the ancient Greek notion of an infinite past and future. Philoponus' arguments against an infinite past were used by the early Muslim philosopher Al-Kindi al-Kindis, the Jewish philosopher Saadia Gaon Saadia ben Joseph, and the Muslim theologian Al-Ghazali al-Ghazal.
Thank you for watching. Consider supporting the channel, leave a like and subscribe.